I'm not sure if this would have been a better lecture to include earlier since you guys are having to actually implement schedulers already. But I mean, you can let me know in the feedback comments on the project if you think this lecture should have been earlier, and the next lecture too. Although the next one is kind of more esoteric schedulers, so you don't have to implement anything from that lecture on the assignment. So we're going to sort of start talking about process scheduling because, of course, the operating system is responsible for making sure all the applications can share the hardware. We talk about that quite a bit earlier on in the class. But the most important hardware resource, and you could say the most limited, because there are very few of them compared to everything else, would be the CPUs. And so the operating system has to make sure that everybody can have a fair share of them, depending on what they're doing, to satisfy various criteria. Sometimes unfair is fine. So yeah, while some processes are waiting for I/O, we want to make sure that the other processes in the system are able to use the CPU, because clearly if somebody's waiting on I/O, they don't need the processor. So we can remember that we categorize processes based on their state. And really we only care about two states for the next few lectures, and maybe blocked peripherally, but we really only care about running, so who's on the CPU, and we care about ready, who could run if they had a CPU, but they don't currently have a CPU. So those are the two process categories we really care about right now. And so the question of scheduling is, how do we figure out who should get the CPU, who should get bumped off the CPU, those kinds of questions. These are really what scheduling is all about. And thankfully, this is a subset of all processes. The ones that are blocked, we don't even have to think about. They get to just sit there and continue to be blocked. Now remember that there's multiple schedulers. We have the long-term scheduler, which governs entry of processes. So this would especially be relevant in a batch processing system. I have 30 processes, or I should say 30 programs all queued up and ready to load, ready to unleash. And the long-term scheduler determines how many should I release, which ones should I release so that I can achieve a good I/O mix, so that I have good utilization of CPUs and good utilization of peripherals. Medium-term scheduler can fine-tune the process mix to make sure that if some processes, I have too many CPU-heavy processes, I will suspend some of them so that there's less pressure on that. We can utilize more peripherals and so forth. But we really don't talk about the long-term and medium-term schedulers anymore. Okay? Now we really focus on the short-term scheduler because that's basically the way that we use computers now. So we're going to, most of our discussion will be on the short-term scheduler. And so I want you to keep that in mind as we're going through things. The other thing is that we're scheduling kernel threads. So remember that a process corresponds to a kernel thread. The kernel thread is kind of the tip of the iceberg into the kernel, and the kernel works with kernel threads. And of course, the user process's behavior affects what the scheduler sees as far as the kernel thread's behavior. We are able to distinguish whether we're executing code in user space or in kernel space. I should say user mode versus kernel mode. The two terms are so similar to each other, user space and kernel. User space and user mode, that it's, you can think of them as being roughly equivalent in this context. Okay, so yeah, the scheduler is going to be working with kernel threads because we've already switched away from the user space program at that point when we're scheduling. Okay, now typically we have a function called schedule or something like that that actually handles scheduling. I say that scheduling and context switching is always performed at a single point in the operating system kernel. This is just to keep it simple. When you have things like kernel preemption, even then you try to set up so that you can enter schedule and have things look reasonable. And again, if you looked at the 7th assignment in CS24, you probably saw that we do a similar thing, except we no longer can do this on a the cooperative basis. Now we do it on a preemptive basis, where we interrupt the user process, we make it look like it called schedule, even though it didn't. We basically update the stack and everything so it looks like it called schedule, and then off we go. So we can do similar things in kernel space, and so we still end up with a single point being where scheduling occurs. So kernel threads, yes, they see themselves entering schedule. They see themselves returning from schedule. Schedule's written in C. So if you're on a Unix-based system, then cdecl rules the day. Now I imagine on Windows you're using standard call or something like that even inside the kernel. Okay, so, but what's interesting about the schedule function is kernel threads, they see themselves calling it, they see themselves returning from it, but we have no idea what happened in between, right? I call it, and then somebody else returns from it, and I don't know it because I'm not running anymore. And then later, eventually, somebody calls it, and it returns as me. So processes, each kernel thread sees itself entering and exiting schedule, but what's usually happening is that we return on a different thread than we start. Now, why would we return on the same kernel thread? Well, if it's the highest priority thread right now, if there are no other kernel threads to schedule, those are the kinds of situations where we might come back on the same kernel thread that we entered on. Now, there's two tasks that need to be performed. One is obvious from the name. It's figuring out who should go next. But the other thing that has to happen is switching from the one kernel thread to the next. And that is a very important detail. So we are going to spend a little bit of time talking about it. Not a lot. Thankfully, this is mostly handled for you in Pintos. And you already got to see enough of this in CS24 that we don't need to beat you over the head with it. But that second part, switching from one kernel thread to another, is typically called dispatching. And it's handled by the dispatcher. The dispatcher is responsible for restoring the new kernel thread's CPU context. Okay? And so, like I say, if the new kernel thread has a user process or user thread associated with it, then we need to go ahead and restore the user configuration so that it looks like the process should when we get back to the process's execution. Okay? So we want the dispatcher to execute as quickly as possible. We are not allowed to waste cycles here because this is an unavoidable step and it is only overhead. So we don't do any thinking, we only do. Maybe, if we're definitely switching to a different process, then we have to update the memory management unit. So we have to change the page table. We have to flush the translation look-aside buffers. If we are staying within the process, just switching to another thread, or we're going back to the same process that called in, then we don't have to update the MMU, so we skip those steps. We always have to update register state, those kinds of things. We have to make sure that we do those things when we dispatch. So what can we do? We just try to make that as fast as possible. Now, an unusual detail that I thought was worth mentioning in class was that switching between kernel threads actually involves 3 threads, not 2. You think, okay, I'm switching from A to B. Okay, well, where's this third thread come from? And you notice it immediately when you look at the dispatch code from Pintos or from any operating system where you can look at the source code. You see switch threads, you have current and next, and then we return a thread star as well. Why would that be? Okay. And so you have to look at this. And again, when you look at these kinds of things from the standard application programming perspective, you say, this makes no sense. This is why I don't want to program kernels for a living. I want to stay in user space because it's much safer. Okay, but we return a thread star because you have to think about what does the thread coming in see and what does the thread leaving see? Because remember, we have a certain machine context when we enter this function, and then when we leave, we're in a different machine context. So what does that other machine context have for switch threads? So notice I switch from thread A to thread B, so I call switch threads A, B. This is not necessarily exactly how the code would look, but we're just illustrating. And so the function switches from thread A's context to thread B's context, which means the stack changes, the registers change, and so forth. Now we're switching from one kernel stack to another kernel stack. We're still in kernel mode. So when thread B resumes running, we're still inside switch threads, but what arguments does thread B see on switch threads? Yeah. Yeah, that's exactly right. When B resumes running, it's going to see itself as the current thread, and whatever guy the scheduler said to switch to next is going to be what B sees. So what happened to thread A? That's the issue. Because what if we're switching to thread B because kernel thread A is ready to terminate? We need to clean up. Or other issues like that. We need to make sure that if, what if we are switching away from thread A because it's now blocked and we need to put it into the appropriate blocked queue? So we can't lose thread A in this dispatching process. That's why we return a thread star. Okay? So yeah, like I say here on the slide, it was switching away from thread B to some other thread C, so we'd see switch thread B and then something else. We don't know what. Perhaps A, but we have no idea. And so it's, if you just relied on the arguments, you lose the thread that you're switching away from because the machine context no longer holds it. It's whatever it was on B when we switched away from B. Okay, does everybody understand that? Hopefully, it's a pretty straightforward thing when you see it. But every time I present this, every year that we teach this class, people are like, I don't know. Oh, I see now, because we're actually changing machine contexts in this function. Okay, so this is the thread switch function. So basically, we need to make sure that we don't lose the current thread, or I should say the old thread that we're switching away from. So because of the reasons that I stated before, we may have cleanup operations we need to do because the thread's terminating. We may need to put it into blocked queue, some other thing. We have to make sure that we don't lose those things. So what switch threads does, there's a little bit of setup code to make sure that the thread that comes in, the current thread, is going to be returned to the caller, even though we're switching contexts. So if you look at the Pintos implementation, what it does is it squirrels away current into EAX, and then it goes ahead and does the machine context switch. So that even though current and next change, we switch from A to B, and then suddenly after the switch, it's B and somebody else, EAX still holds A, and that gets returned, because remember, with cDecl, EAX is the return value, and then that way we can still get to the old thread when we return. Okay, any questions? Now, is that really critical to anything you have to do in Pintos? Not really, but if you actually follow the advice of the assignment and walk through a context switch, then you may have come across this code, and that's the reason why we have to have 3 threads instead of just 2 when we do a context switch. All right? Now you know. Okay, so getting back to scheduling, there's a lot of different ways we could evaluate scheduling algorithms. So I say measures to evaluate scheduling algorithms with. So we could look at how busy do we keep the CPU. That's one thing we could do. We could say how many processes do we finish in a certain amount of time. That could be another measure. Turnaround time, how long does it take to finish a particular process? We could either take a specific process or a specific kind of process that we want to finish quickly, or we could say, on average, what's the turnaround time of the scheduler? How much time does a process spend in the ready queue? I.e., it could run, but it's not getting to, so it's frustrated. If it had the CPU, it could feel frustration, but it doesn't, so it just sits there. And then response time. How quickly does the process begin producing output? Sometimes you see that as a goal, but not always. So you can imagine that of all of these various measures, we could try to optimize for any number of them. Maybe just one, maybe a bunch. So scheduling algorithms, there's many different scheduling algorithms that you could look at. And a lot of times when you see scheduling algorithms and operating systems, they are in the family of the scheduling algorithm we talk about, but then they have various tweaks that are hopefully going to improve various things that the operating system is trying to achieve. Okay, so processes themselves. Processes tend to have times of computation, periods of computation, followed by periods of I/O, and then periods of computation, and then periods of I/O. Compilers are a great example of this. I load a file, I parse it, okay, I need to load this other file, so more I/O, and then I parse it, and so forth. And then I start generating, abstract syntax trees, and I try to, do high-level optimizations, blah, blah, blah. Now I'm in memory. I'm, using the CPU, and then I write intermediate results out to disk. Well, that's going to be another I/O burst. So you can see that processes tend to do a bunch of computations and then a bunch of I/O. And there's a significant amount of research about this. It's kind of interesting because how you get these measures is interesting as well. you can imagine if you have an operating system kernel, then you can instrument the kernel to figure out what are these behaviors. So that's kind of a fun thing to explore. That would be a great little project to try to reproduce some of these measurements. But anyway, like I say here, the research usually characterizes the distribution of CPU burst lengths as being exponential. So you have a lot of really short ones, and then it falls off. You have relatively few that are actually long CPU bursts. We have schedulers that are cooperative, which basically means that they don't schedule very much. They basically only decide who should run next when the current process kindly releases the CPU. Okay? So again, this was how early Windows behaved. This is how early Apple operating systems behaved. And it's a pretty simple thing. You know, a lot of simpler operating systems have this approach. I got to work on a computer system that unfortunately is no longer available here when I was an undergrad, and it had a very simple operating system with a cooperative scheduler, so you had to behave or else the system would lock up. But then you have schedulers that are more aggressive and will actually preempt the current running process if it spends too much time on the CPU. Okay, so most of our schedulers now are preemptive because they just are more, you know, they're more robust in the context of programs with bugs, which it turns out happens from time to time. Okay, so simplest algorithm, first come, first served. Why do we even talk about this? Well, really, just because we want to set up where round robin scheduling comes into the picture, so it's not very interesting. But basically, the ready queue is just a FIFO. Whatever goes in first comes out first, and it gets the CPU as long as it wants it. When it's done, when it does something that causes it to block, or it yields, or it terminates, those are sort of the three events that we care about, blocking, yielding, or terminating. Then it gets off the CPU, and the next guy that's at the front of the FIFO gets the CPU. And obviously, if it blocks or yields, it goes into the appropriate blocked queue, and then enters the back of the FIFO, and then walks all the way up to the front again. Okay. So first come, first serve, not preemptive, not very exciting, but it is a really simple scheduler to implement if you don't want to have to think very hard. And again, writing an operating system is complicated enough, so you can always start with first come, first serve, and then make it more intelligent later. Okay? And it turns out that this actually does pretty well a lot of the time because most programs eventually do an I/O burst, and so they get blocked and they get out of the CPU and let somebody else run. So, like I say here, it's good for batch processing because typically you don't have a lot of interaction and you just want CPU tasks to complete as quickly as possible. It's bad when you have programs that don't terminate, which is not a surprise. And if you need responsiveness, first come, first serve is terrible because we have no preemption, which we really would need for good interactivity. Now, if we add preemption based solely on time slices, then we get round robin scheduling. Okay? So now we're saying you can have as much time as you want as long as it's less than this amount, and then you get booted off the CPU and somebody else gets to run. So the ready queue is still a FIFO, and again we have block, yield, or terminate, but then we have another criterion which is you used up your entire time slice and then you get booted off the processor as well. So this is now a preemptive scheduler just by adding this little facility, and if it gets preempted then it goes back to the end of the FIFO. If it yields, it goes back to the end of the FIFO. If it blocks, then obviously we all understand what happens there. And we have a really interesting knob, which is this time slice size. What do we do with that? Well, if you give everybody a large time slice, then batch processes love it because they're going to get a large amount of time uninterrupted. And obviously, if you had a whole bunch of CPU-intensive tasks, you'd get very few context switches. Remember, context switches are overhead, so the less we do that, the more CPU time we have for computing. Then, so that's nice, but it's terrible for responsiveness because you have to wait for all the CPU-intensive tasks to get their time. And interactive processes, since they have small CPU bursts, we could have a very short time slice, and then we're wasting a lot of time context switching, but the interactive processes fare a little better. So this is round robin scheduling. Does anybody have questions about this? I know we talk about it in CS24, so it's not new or particularly exciting, right? It's like, okay, great, round robin, woo. Okay, shortest job first. We also talked about this one. And I have this little note here that, we call it shortest job first in the, in CS24, but really what we're talking about is how long will the next CPU burst be, okay? Because really we expect the program will have multiple CPU bursts. It will eventually block an I.O., and we'd like to estimate, well, how long does it take to get to the next I.O. burst? That's really the amount of time that we'd like to estimate. And so this will minimize the average waiting time of processes. So again, we had this example in CS24. If we have 4 processes with these expected CPU burst times, so 2 units, 4 units, 5 units, and 7 units, and we do them shortest to longest, then we get an average wait time of 4.75. And if we order them in the opposite order or any other order that's not shortest to longest, then we see that our average wait time will get a lot longer. So 0, 7, 12, and 16 has a significantly higher average than the shortest to longest ordering. Okay? So that's the idea behind shortest job first. But of course, how do you actually predict the length of the next CPU burst? That's kind of like reading the future, and we have demonstrated in general that we're not very good at that. So we have to basically predict it using past behavior, which is usually a pretty good indicator. But the problem is sometimes we have programs that change their behavior dramatically as they execute. And so we'd like to make sure we don't put too much weight on, distant history, and we'd like to be able to consider recent history a little bit more strongly, like give it a little bit heavier weighting. And so typically you'll see these systems use an exponential average. Okay? Now, when I was staring at my slides this morning, I totally didn't notice the difference between T and tau, and I'm like, why is that even interesting? But tau is very important because tau captures the historical behavior. T is the most recent amount of time that the process ran before it finished. Okay, I shouldn't say process. It was the time of the most recent CPU burst. Let me say it that way. So the process hasn't terminated yet. And so we have this alpha, which is a value between 0 and 1, and it allows us to weight the most recent one and the historical behavior. So we have this nice knob that we can turn and sort of see what do we want to actually weigh. If alpha was 1, we would only look at the most recent. If alpha was 0, we would only consider historical behavior, which I guess would eventually include Tn because we update tau based on the various, basically the whole history of the process's behavior. Okay, so expanding this, tau of n plus 1 is going to be alpha times tau, or Tn, plus 1 minus alpha tau n, and then you can go ahead and expand what tau n would be. And you can see that you get this thing, and if you keep going, then you end up with seeing where the exponential average term comes from. You have this 1 minus alpha, which is, you have the first term is 1 minus alpha. Well, I guess let me make sure that I don't say this incorrectly. So yeah, you have 1 minus alpha, then 1 minus alpha squared, all the way up to 1 minus alpha to the n plus 1. And so you can see it gets smaller and smaller as we shrink that, because alpha is between 0 and 1, that's going to shrink as we get further and further into the past. Okay? And so tau 0 is just the original guess of how long we think the process will take. I don't know how we guessed that. I'm sure somebody has some clever thoughts on how to do that, but I didn't bother to read into it. Okay, so but this is how we can sort of come up with a guess as to how long the process will run for its next CPU burst. Okay, now we can either make this preemptive or non-preemptive. And obviously if it's preemptive, then if some blocked thread or blocked process became ready, so it was blocked and it becomes ready, and it happens to have a shorter estimated runtime, remaining time left to run, then we want to go ahead and bump it to the front of the queue. So it might actually preempt the current job on the processor. Okay, so we call that shortest remaining time first, because the guy who was running will become ready and it will still have some remaining time left. So we put it back into the queue. And of course, we also talk about this in CS24 that shortest job first can have starvation issues if you have long processes and basically short processes keep showing up. So if you have short jobs, I should say that we keep having a process's behavior where it keeps becoming ready quickly, so it keeps having short CPU bursts, and it keeps becoming ready frequently, then it could starve a long-running job from ever actually getting to the processor, which is no good. We want to try to make sure that everybody eventually gets to run, or else you'll have processes that never actually finish. Okay. Now, are there any questions about this? That's basically all I'm going to talk about with shortest jobs first. It's mildly interesting. Thankfully, we don't have to implement it. I don't know, it looks really boring to me to implement that exponential average stuff. But shortest job first is a simple example of priority scheduling. We're actually going to talk about priority scheduling. Like probably the second time I taught this class, people were like, why do you have to why do we have to implement a priority scheduler? Who actually uses priority schedulers? Well, it turns out a lot of space probes use priority scheduling, which we'll talk about. But priorities are actually important in most of our scheduling algorithms. So it's kind of nice to have a basis of being able to have the simplest kind of priority scheduling as part of your experience. So shortest jobs first, though, you can think of it as being priority scheduling because the shortest job has the highest priority. It always gets the CPU first. But we can also give processes fixed priorities, which is something you all have to do on this project. And typically it's just a number, and of course, should the lower number be higher priority? Should the higher number be higher priority? Well, operating systems have historically been all over the map on that. So I can't remember. I have some examples toward the end, and Linux and Windows, as usual, do it the opposite way of each other. But yeah, you can either have preemptive or non-preemptive priority scheduling, which again, in Pintos, what you have to implement is preemptive priority scheduling. So if we have non-preemptive, then when we get a new high priority process, it does not interrupt the current process that's running. Okay, so that's non-preemptive. Preemptive just means if a new higher priority process joins a ready queue, it gets to go to the front. It gets right onto the CPU, and the lower priority process is bumped off. Okay. Typically, interestingly enough, we do not enforce time limits. So again, I hold the CPU until I yield, block, or terminate. Now obviously, if I yield, then I'm going to get it right back unless there's other processes with the same high priority. Typically, the way these systems work is if you have a bunch of processes at the same priority, it'll just round robin them. So yielding in that context would make sense, but if I'm the only process at the high priority and I yield, then I get it right back. So it's like, okay, that was interesting. So anyway, those are some of the details there. Let's see, yeah, priority scheduling is vulnerable to starvation. Okay, that's by design, so you can design systems carefully and make sure that that doesn't happen. You make sure your high priority processes always eventually block on something, maybe on the timer because they need to wait for something else to happen. There's some interesting approaches that you'll see in people who have implemented priority scheduling. You can age processes, so the longer it's in the ready queue, you just sort of like slowly bump up its priority until it finally is high enough priority that it gets the CPU. So that's one thing you can do to keep starvation from occurring in priority scheduling. And of course, the other one, which we talk about quite frequently, is priority inversion, where you have an interesting situation that can occur where a lower priority process will prevent a higher priority process from ever getting the CPU. Okay. So like I say here, higher priority processes, what's supposed to happen is the higher priority process is supposed to preempt the lower priority process, but we see that not happen. Okay. And this is the classic scenario. You see it in the literature that discusses priority inversion and so forth. So we have a low priority process running and it locks a shared resource. Then the high priority process starts running. It would like to acquire resource R, but it's not able to. So it goes ahead and blocks, and since it's blocked, it's not able to do anything. So we resume L, which would be fine. This, if this were the whole world, then we would just keep running, and eventually L would finish and H would preempt, and off we go. But the problem is, then we have medium priority process M step into the picture and mess everything up. M4 screws it all up. So anyway, M doesn't need R, and it can run as long as it likes because we don't have any preemption in priority scheduling, and so it runs indefinitely, and L is blocked indefinitely, and thereby H is also blocked indefinitely, even though we'd like to actually get H its resource so it can finish. Now, typically, and so the reason why this is actually a problem is because typically high priority processes are given really important things to do. Okay? Some of you may have taken CS24 where I used the Mars Pathfinder problem, and so you'll actually get to see that. We'll talk about that briefly in a moment. But, if they have this situation where the high priority process is taking care of system critical things and then they're starved out by some lower priority process that can run a really long time, then our system can basically fail. Okay, so Pathfinder was, so 1997, that was a year before I was going to graduate college. I was like, it was junior year. I remember it sucked because I was here. So anyway, and Pathfinder got launched, and everybody was excited. Like, what are they, is this thing going to even work? Because instead of, like, having rockets and stuff, we're going to make, we're just going to surround this probe with air balloons, and it's going to bounce all over the surface and then open up, and yay, this is going to be cool. And a whole bunch of people were like, no, it's never going to work. So it was exciting. And so everything worked out how it was supposed to. This thing opened up, and the rover drives off and everything. But then what happened is we started hearing news reports that the thing is rebooting all the time. Okay, well, that's not a good sign. So what's going on? Well, it turned out that it was actually a priority inversion issue on the rover. Okay, you had the high and low priority processes sharing a common resource that they both needed to lock before they utilized it. And the high priority process was responsible for resetting this watchdog timer. The idea behind a watchdog timer is if it counts down to 0, then it reboots the system. And what's supposed to happen, if everything's working right, is periodically some high priority thing goes and resets the watchdog timer so that it doesn't actually hit 0 and reboot the system. That's a way of telling that the whole system isn't wedged. Okay? But if the whole system is wedged, then it's not going to get around to resetting the watchdog timer, and it hits 0, it resets the system, and it comes back, and it's like, oh, I must have wedged myself or something. So that was the idea. But what was happening is the Pathfinder was rebooting all the time. Well, the medium priority process was doing something like weather measurements or sending data back to Earth, which tend to take some time. And it didn't require any locks, but what it was doing was preventing the high priority process from resetting the watchdog timer. And so the thing kept rebooting, and they're like, okay, the thing is only like a few million miles away, so how are we going to actually solve this problem? Okay. Let's see. So I just wanted to mention just a few other details about this. You might say, how could the likes of JPL screw something like this up? And, I don't think that's actually a very fair question because it's surprisingly complex. But the operating system that they were building this on is called VxWorks. Has anybody heard of VxWorks? So it actually is an operating system that is used for a significant number of these kinds of projects. And it has a very simple priority scheduling system for managing multiple jobs. And it has the ability to, have this problem. But it also had a solution implemented which they just left off. And we'll talk about why when we get there. So I'll just sort of use that as setup. Now, various solutions. One is random boosting, which to me seems crazy, but that's what Windows decided to do for the priority inversion issue, which is basically, well, if we have a problem where it's actually, we have a priority inversion, let's just bump up stuff so that eventually it will get a high enough priority that it will get to run again. So basically, it's ready, but it's preempted. Then I'll go ahead and randomly bump up its priority until it exceeds the priority of other things, and then that'll hopefully resolve priority inversions if they occur. Thankfully, I don't think it does this anymore, but that's how it solved these kinds of problems back in the day. You also have another one, which is pretty interesting, a priority ceiling protocol, which is probably the lightest weight approach that you could choose to solve priority inversion, where basically resources are given a ceiling priority, which is the highest priority of anybody that's allowed to lock that resource. So that's the hard part, is figuring out what is the highest priority of any process that can lock this resource. And when a process locks the resource, it automatically gets the priority ceiling for that resource. Okay? Obviously, if you had like 5 resources that you could lock, you lock 1, 2, 3, 4, 5, you get the ceiling, which would be, the highest of all of them. But priority ceiling protocol is really lightweight and really simple. And some of you who have implemented the priority donation mechanism now probably can see how this would be much, much lighter weight to implement. Okay, so priority donation, aka priority inheritance, is the most sort of general purpose, but it's also pretty costly. And so like I say here, if a high priority process is blocked waiting for a resource held by a low priority process, we donate the high priority process's priority to the low one. So that should bump it up over anybody in the middle who's keeping everybody from moving forward. Okay? Now, typically we choose the maximum. If you choose the sum, which is possible, then you can run into issues with having other weird priority inversion issues. So basically, typically the maximum is what is used when you are going ahead and assigning a priority. Okay. Any questions about any of these? All right, so we'll go ahead and keep going. Yeah, priority donation does have some issues. A lot of times you'll have process waiting on process, waiting on process, waiting on process, and you have to go all the way down that chain. Yeah, so 2 locks R2 and then wants to lock R1, 3 locks R3 and then wants to lock R2, and blah, blah, blah. So if process 5 is high priority, then you have to make sure process 1's priority is updated to reflect everybody in between. Okay, so that clearly takes some time. So this is serious overhead. And this is also, as an aside, why JPL left priority donation off in VxWorks when they sent the rover up to Mars. Because they're like, this is a lot of overhead. We've never seen this problem in real life, so maybe there isn't a problem. But, so they don't just turn things on because it might be a good idea, because, when you send a space probe far away, you don't have, you don't want to be taking very many risks. Okay, so this is a huge overhead that can be imposed by having to deal with these kinds of situations. You also have deadlock issues that can occur, and your donation mechanism, it's not like deadlock is okay. Deadlock is still a bug in your system when you have deadlock in these situations, but it causes the failure in a new way. So process 1 locks R1, 2 locks R2. Process 1 wants to lock R2 and block, so it donates its priority to process 2. So far, in our graph of who's waiting for whom, we have no cycles. So that's fine. That's a really quick, simple thing. And then process 2 attempts to lock R1 and blocks. And it's weird because now it sees itself waiting for itself. Okay? So the priority donation mechanism needs to be clever about detecting cycles. Or else, when you have a deadlock between processes, what happens? Well, instead of everybody grinding to a halt and waiting, now you see spinning in the kernel following the cycle. Okay? So that's no good. And so basically, a priority donation mechanism should also be able to detect deadlock so that it can actually say, hey, this bad situation came up, and y'all are messed up, and so you need to fix your problem, but I'm not going to hang. Okay, so that's kind of the issue that you have when you have a cycle in this graph. You can run into big issues. Okay, any questions on any of these things? I don't think you guys have to deal with that in Pintos. Yeah, which is good. Yeah, did you have a? Yeah, no, I don't think there's any tests, right, that actually do that. That would be really awful. I would fly up to the Bay Area and smack the guys that wrote Pintos if that happened. I wouldn't really. I don't want to spend the money on a plane ticket. All right, so enough about priority scheduling. Now, there's a couple of multi-level queue scheduling algorithms that we're going to talk about. One is the one you have to implement, or at least the basic version of it, because we're not going to go into the BSD scheduler because you have documentation for it. But basically, if you look at processes and how they behave, you can kind of categorize them based on what they do. So you have system processes, let's say they're critical things, interactive processes, interactive editing processes. Why would you make that distinction? Well, maybe one, you expect to be getting a lot of input all the time, but editing processes, you expect that the person's going to be staring blankly at the computer at times as well. So maybe a slightly lower priority. And then batch processes as well. So those are CPU intensive. Okay. Now you can also look at them from a standpoint of general categories. So I have things that are occurring in the foreground because they need to interact with the user. We'd like them to be responsive so users don't get angry and throw the computer. And then background processes have large CPU bursts and are not interactive. So this is multi-level queue scheduling. Notice it is not multi-level feedback queues. You'll notice that what we do is we actually assign processes to a queue and then they do not move from that queue. So we just have to pick a queue based on what we think the process needs. So queues have a decreasing priority. The highest priority queues are always going to be pulled from first until all of those processes block, and then we'll go down a priority level and blah, 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 all the way to the low priority queues. Okay. And so you can see that if you do this assigning badly, then you have terrible problems, because if you put a batch process into a system process queue, your whole system suffers massively from it. Okay? And sometimes people would do that. It was definitely possible back in the early days of Windows that you could say this process is super high priority, except it's computing, and now it's higher priority than the thing that handles the mouse moving. And the whole system is like horribly non-interactive after that. So you could do that kind of stuff. So highest to lowest, yeah, and queues have their own priority. And typically the way this works is if there is a runnable process in a high priority queue, it gets the CPU right away. And again, why do we do this? Because we're trying to maintain responsiveness. We're trying to make sure that critical system tasks happen. Okay, so that's why this is typically a preemptive scheduling mechanism. And the other aspect of this is we expect that the higher the priority, it has to happen and it will be short, so it's not going to hold the CPU for very long, or we expect it's interactive and it's going to block really quickly. So that's why the whole system behavior doesn't suffer when we move these things into the high priority queues. Also, you will sometimes see these multi-level queue schedulers try to subdivide CPU time across different queues. So they sort of say, you know what, we want to make sure that the bulk of our time is spent running from these queues, and then some much smaller percentage will be used for lower priority items. So this is the idea of multi-level queue scheduling. It's kind of like the first come first serve scheduler. It's like, okay, I can see that this is the basis of something else, but by itself it's kind of limited and it's not very effective. Okay, so queues can have their own scheduling algorithms and parameters. So if you had real-time processes, they needed to get real-time scheduled on the CPU so that you could make sure that those things always get to run at a specific time frame. Then you could have a scheduling algorithm for that. I mentioned batch processes. Okay. Anything that doesn't fall into these categories, you might just do round robin from its queue, so that's not a big deal. And the reason why this is lame is because processes frequently change behavior over time. It's not uncommon for this to occur. Now, it's also really common for a process to stay the same all the way along. I suppose something like a web browser would be a great example where virtually all of its life is spent just being an interactive process. Microsoft Word, the bulk of its life is spent being an interactive process. Okay? But then there's plenty of examples of processes that don't behave that way. So MATLAB is a great example. One of my favorite programs ever, right? So I sit there, I write my MATLAB program, and then I run it for 2 hours, and so I walk away and do something else. It switches from being an interactive process into being a batch mode process or a compute intensive process. Photoshop is another great example. Handbrake, which I use for transcoding the recordings, all of that kind of stuff, interactive, and then it switches over to being compute intensive. Okay. So multi-level feedback queues are basically multi-level queue scheduling plus the ability to move processes between priority levels. That's really all we're adding here. Okay, and thankfully we already talk a lot about this in CS24, so we don't need to beat it to death. But basically we want to favor the short jobs, the ones that block, yield, or terminate quickly, because we want to make sure that they get the CPU quickly, so we make sure that they get high priority. This will approximate shortest job first scheduling. And if we have processes that block frequently on I/O with short CPU bursts, then we can presume pretty well that they are probably interactive processes. Okay, that's a pretty safe bet. When you press a key, a whole bunch of stuff happens, and then it blocks again on the keyboard. Press a key, a whole bunch of stuff happens, and it blocks on the keyboard again. When you have that kind of behavior, it's a safe bet that it's an interactive process. And so then we can basically separate processes based on their runtime behaviors. Now there's another goal here, which is that we'd like to have few context switches for longer running tasks, CPU intensive tasks, because they hate context switches. So that is also sort of a goal that falls out of this. Thankfully, it's just sort of automatic based on these other goals. Okay, so we have multiple FIFOs for processes. So again, we have a queue for each priority level, but they also have some time limit associated with the queue. Okay. And so what we do is we put a new process. Typically, I shouldn't say the highest priority queue because that may be reserved for system or real-time processes or something like that. But there will be a highest priority queue for applications. We just stick it there. Okay? And it will eventually get to run, and then it'll either be preempted because it took too long, or it'll block on I/O. So then we can go ahead and make our decision about what to do next. So if the process yields or blocks, then it goes to the end of the same queue. If it gets preempted, then it's bumped down a queue level. And if you have a low priority process that is starting to behave like an interactive one, it could be moved up. So if it stays within the time slice, let's say a few times, then go ahead and bump it up to the next queue. So what happens is processes get sorted into queues based on their behavior really quickly. And the queues are prioritized, so now we get a nice system that favors interactivity, favors short CPU bursts, but still will not context switch away from longer CPU burst processes if nobody else is ready to run. So that's kind of the idea behind multi-level feedback queues. Okay, so how many queues to have? That's obviously one option for what do we do for this scheduler. Another thing that's nice that you can tune about it is you can pick different scheduling algorithms for different queues. That's really valuable. Most operating systems leverage that. How do you decide which queue it goes into? Well, like I said, depending on sort of the general category, if it's a system process, it'll go into one set of queues. If it's an application process, it'll go into another set of queues. If it's a real-time process, typically it'll go into a different set of queues. So that's nice. And also these decisions about when to promote and demote, you can come up with clever rules for that as well. So you have all of these options with multi-level feedback queues. And so that's why these are used in most operating systems. Okay, not Linux. Linux is very interesting. One of the things that I really love about Linux, it's just like we talked about read, copy, update last time. Linux is a real tremendous test bed for trying new operating system ideas. And you see that a lot. Let's try a new scheduler. Okay. That didn't work out. Let's try a new scheduler. Okay. And so that's why Linux has actually been through a number of very interesting schedulers that we're going to talk about next time. Same thing with read, copy, update. Let's try this innovative lock-free coordination mechanism. Okay, hey, this is really working. Let's adopt this, and so forth. So it's nice to see that there's places where you can sort of innovate and have a lot of flexibility. Okay, so here's a few details. Windows NT, Vista, and 7. I've been told that 8 and 10 also behave this way, but I can't guarantee it. But you have 32 levels, and you can see that the lower the number, the lower the priority. So 16 to 31 are the soft real-time priorities. OS 10 has, interestingly, 4 priority bands. So it's not quite exactly multi-level feedback queues, but it's along the same idea. So you have normal, system high priority, kernel mode only, and real-time threads is the very highest priority. And the threads are constrained to be within their priority band. So obviously a real-time thread is never going to be demoted into kernel only. That wouldn't make any sense, and so forth. So that is one of those nice things about multi-level feedback queue scheduling. Various BSD Unixes have a lot of queues. Various categories. So again, you can sort of pick a category, or I should say you can pick a queue based on the category of process and start it there and retain it in a band if you need to. And Solaris, what's Solaris? Does anybody here run Solaris? Okay, that's okay. You don't really need to. You know, sometimes I say if you haven't done X, then you haven't lived. You can live without running Solaris. That was one of the first operating systems I had to actually program on, so it was kind of fun, but who cares? Anyway, but it also has 170 keys. But you can see how we have these different operating systems that would use these various variants, basically, of multi-level feedback queue scheduling. Very, very popular scheduling. Linux used multi-level feedback queues up to Linux 2.4, and then it started really exploring various things. So what we'll do next time is one of the coolest things that I think scheduling related that you can look at, which is real-time scheduling. We talk about shortest deadline. No, what is it? Shortest deadline? I can't remember exactly what we call it. But anyway, we'll talk about it. Earliest deadline first scheduling and how badly it breaks. I can't wait to talk about it. It's really cool. And then we'll start talking about how current Linux schedulers work as well. So we'll talk about that all on Wednesday.